All right, so this will be galvanic cells number 2, which is basically going to be an example problem. So if you haven't seen the first one, it would be wise to go back and watch that before you start this one. And we're just going to do another example practice problem. If you feel pretty good about the one that we did in example problem number 1, you may want to skip to galvanic cells number 3, because in that one we're doing the acid, which is a little bit different. So before you start them on your own, make sure that you've watched that. All right, so in our next galvanic cell problem, we're going to do a lead and silver cell. And so this is going to be a galvanic cell. And so in order to have a galvanic cell, you have to have a positive E cell value. And so we know that one of these has to get oxidized and one has to get reduced, but we're really not sure which one. So let's try it out. All right, so for oxidation, we'll go ahead and just try out silver. So if silver is getting oxidized, it's going from the metal to silver plus 1, and that's going to produce 1 electron. We look it up on the table, it's 0.8, so that's going to be negative 0.8 volts since it's oxidation, not reduction. And for the reduction half, if silver is getting oxidized, then the lead has to be getting reduced. And then when it's getting reduced, that means it's going from the ion, picking up electrons, going to the metal, just like in single replacement reactions. So it doesn't matter which one you start with being oxidized and which one you be reduced, because we're just going to keep working on it until we get a value that is positive. So one way has to work and one way won't work. So we'll know right away when we add this up. And let's see, lead is negative 0.13. So obviously when we add these up, we're going to get negative 0.93 volts. And that is not going to work. So now we're going to have to flip this over and try this the other way. So now we're going to do oxidation is the lead. So if lead's getting oxidized, we start with lead metal. We're capable of doing that because we have both lead and the lead 2+ in the solution. That's the big difference between a single replacement reaction and a galvanic cell, is that you usually have both. There are more complicated galvanic cells, but in some ways they're almost easier because you have to be provided a lot more information, even though the reactions are more complicated. And I just drew that 2+. Was not paying attention. So that's going to be lead. It's getting oxidized. That means that it's the lead metal going to lead 2+ plus 2 electrons. And that's going to be positive 0.13 because you flip it over. And then reduction is going to be the silver ions in this case, picking up an electron, turning into silver metal. And that's going to give us 0.8 volts. So when we add that together, our overall E cell is going to be 0.93, oops, I forgot the 3 volts. And we will only get that E cell if, and only if, we have standard conditions. So both the solutions are 1 molar, it's a 1 atm, and the pressure is, or the pressure is 1 atm and the temperature is 25 degrees C. All right, so now let's look at adding these two reactions together. We can't because the electrons here are 2 and the electron is only 1 here. So we need to multiply this through by 2. You have to multiply all of them by 2. And now we can add these together because the electrons cancel out. So we have lead plus 2Ag gives us Pb2 plus 2Ag, and that's our overall reaction. Now I'm going to clear the screen and just bring these two values over because we obviously don't need this because it didn't happen, and so that we can start setting up our drawings. Okay, so I'm going to transfer this over. We had silver added to lead. The lead is getting oxidized and the silver is being reduced. Okay, and our voltage was 0.93 volts is our standard E cell. That cell, just not written very neatly. Okay, so when we draw this, we're going to draw 2 separate beakers. Now, sometimes, what's kind of interesting is, sometimes these aren't completely separate from one another. Sometimes they'll actually sit directly next to each other. And I'm going to draw it that way just so you see one of these. Instead of them being sort of like two separate beakers, it's actually like one giant beaker and it's separated by the salt bridge. So in this case, the salt bridge is in between. It's a porous membrane that makes it up. And so it allows the ions to flow through here, but doesn't allow the two solutions to mix. So this is kind of a one container setup versus a two container setup with something splitting it down the middle. And in this case, this whole bridge doesn't have to be made of NaCl. So we're going to make this one out of KNO3. And I'm choosing NO3 because if we look here, both these ions are NO3, and so we know that they're not going to cause any sort of secondary reaction. Sometimes Cl will precipitate out and stop your cell from working. So you'll often see KNO3 as a salt bridge option. So over here, I'm going to put our lead. So we've got our lead electrodes. This will be an actual solid piece of lead. And this will be in lead 2+ solution. And we'll have a spectator ion, kind of draw that off to the corner. And then this will be clipped onto a piece of wire. And that will be connected on the other end to the piece of silver. And this is floating around in Ag+, and there's more spectator ion in there. Okay, so let's figure out which one is our anode and which one is our cathode. So if we look here, the silver ions are going to silver metal. So over here, this is where reduction is taking place. And it doesn't matter which side the oxidation is on and which side the reduction is on. You just have to label it. So reduction is our cathode. And let's draw our little arrow. So what this is basically telling us is this solution, the dissolved ions are coming out of solution and plating on top of this piece of silver. So your mass of silver, the mass of Ag is going to be increasing, and the molarity of the Ag+ is going to be decreasing because it's getting used up as we do the reaction. We come over to the other side, the lead is not coming out of solution. The lead is, the lead is going into the solution. So the lead is turning into lead 2+. Okay, so that's what those arrows are showing us. And this is where oxidation is taking place. So this is our anode. Okay, and in this case, as this cell runs, the mass of the Pb is going to decrease because it's getting used up. And the molarity of the Pb2+ is going to increase because you are producing it. That's what these arrows, that's not an AP thing. That's a Miss Rodebe thing. But these arrows really help us to see, of course, if they're better arrows, they really help us to see what's actually going on in the reaction. All right, so we now have labeled that. We need to come back and show where the electrons are going. So the electrons are going from the anode, because that's where the electrons are being produced, to the cathode. That's what these arrows mean. That's our flow of electrons. Flow of electrons are going this way. If we were to put a voltmeter on this, which I didn't draw, but if you want to, you can put a little voltmeter here. V is usually the symbol. If it's a standard cell, it should read this voltage, but it will only read this if our molarities are 1 and we meet all the standard conditions. The last thing that we need to look over is our salt bridge. All right, so for this salt bridge, over on the cathode side, the Ag ions are being lost because they're turning into silver metal. So we need the potassium that's in this porous membrane to go over to the cathode side, because remember, the cation will always go to the cathode, and that's to replenish the positive charge. Because again, if we allow this to be lost, we're going to build up a negative charge on this side, and that's going to stop the reaction from happening, because a circuit can't be complete without it being a completed circuit. And that's what the salt bridge's purpose is, to complete the circuit and make sure we don't have a buildup of charge on either side. So we already have NO3 hanging around, but if we see here in the salt bridge, this will move over. So NO3 will move over this direction. okay, as part of the salt bridge, and that will balance out the extra positive 2+ lead ions that are formed as a result of the reaction. And that's your entire cell. So the last thing to take a look at is some conditions where the voltage would be more than or less than 0.93 volts. So let's take a look at a couple of conditions. So let's say that we had one where you had 2 molar lead 2+ and 1 molar silver 2+. Okay, and so when we look at this, we have to look at which one is the reactant and which one is the product. So in this case, the lead 2+ is a product, right? It's a product. And the silver ions are a reactant. So right now we have more product than we have reactant. And when you have more product than reactant, that lowers the voltage. So it would be less than 0.93 volts. It would be lower than. Well, let's take a look at a different example. So now this time, let's say we have 0.5 molar Pb, 2+, and again, that's on the product side. So the P just needs product. And this is going to be 1 molar Ag+, and that's the reactant ion. And that would increase the voltage because you have more reactant than your product. Anytime you have more reactant than product, it's going to drive the reaction to the right faster, speed up what we call the forwards reaction. And that's going to give you a higher voltage reading than 0.93. How much higher would require the Nernst equation, which you're not required to solve? And just as a note, the original mass of the electrodes, right? So the silver, that would be the Ag and the Pb. They do not affect the voltage, the size of them. So if you make one of those bigger, it doesn't matter because they're solids since they're not in solution. So they do not affect the voltage. They don't have an impact on the voltage since they're solids. So the only things that will affect this voltage is going to be this. You also can affect it with temperature, but again, you'd have to really plug it in to see exactly how that would have an impact. All right, so that's it for this example. The third example is going to deal with a slightly different situation in which you have an acid as one of your cells. Okay.